Okay, so before we get started, I'd just like to say that Eric is having an operation on his hand today, so he'll be out of action for a while. He'll be back next week. And he was involved in trying to grade your assignments, and he did some procedure to download everything, and everything got trashed. He's trying to work with the B-Space people to recover, because obviously they keep backup copies, but short of that, maybe they will have to ask you to resubmit 2 again, so we'll know early next week. So just make sure you hang on to assignment 2, and I guess assignment 3 is going to be due on Tuesday. So we're sorry about that, but B-Space is not a very friendly platform, and in fact, they're trashing it at the end of this year, and we're going to get something better. Colin, did you want to say anything?
Yeah, I was going to say that what I talked about the time is, if you don't file that, if you have something by you tomorrow, that will guarantee that today will be so if you do something with that box by tomorrow, you'll be able to see that.
Okay, so resubmit. By what time tomorrow? Beg pardon? Okay, by noon tomorrow. Okay, great. Okay. So today I'm going to be working mainly on the board, but I've got a couple of diagrams here that we'll work from as well. Okay, have a question? Oh. So at the site, you can download my section on harvesting from this Encyclopedia of Ecology, which I wrote a couple of years ago, and Gordon's seminal paper and Schaefer's seminal paper on which this basic theory is developed. So these papers came out in the early 1950s, and these papers are reissues of the original papers in a 1991 issue of a journal. So you can find those online. I'm going to close this down so that I can use all the whiteboard space, and then I'll open it up as we need it. I guess we've been through this again, so let me see if this... Okay. I'll just turn this off. Lucky you don't have to do this math. Or not. Okay. So last week we were talking about the harvesting model. The x dt is equal to f of x minus h, but for the special case where h is equal to v times x. So how did we interpret v in this model? Yeah? It's the effort, okay. It's the rate at which we apply effort. Hi, why are you guys so late today? Why so late to class? Okay. Everybody seems to be running late. And what we did is we constructed these equilibrium curves where we plotted f of x and h of x equals v times x. And if you remember, if f looks something like this and h looks something like this, then the point where they intersect is an equilibrium, which I can write in many ways, but remember, it depends on h. So the fact that it's an equilibrium, I'll put a little hat on it, and I'll give it a little subscript h to say that it depends on the particular value of h. Now, when we harvest the population at this level, we get a yield, and the yield is the rate at which we extract this harvest, so this yield is h. Now, to denote the fact that this yield is an equilibrium, I'm going to draw what I call the equilibrium yield effort curve. So this is the equilibrium yield effort curve, and I'm going to plot the yield h. So if you remember, we defined the harvest, or the yield, y, and the average yield over time to be the integral of h dt. Now, h could be a constant, then that's easy to integrate. And in this case, if it's sustainable, then it's a constant. So to denote that this is sustainable, I'm going to have a little hat on it, and I'm going to subscript it with v, because it depends on v. And here, I'm going to plot v, my effort. So when the effort... Sorry, this is v times x, not h times x. When v is 0, I'm right down there. When v is 0, what is the rate at which I'm extracting a resource? How much resource am I getting per unit time when v is 0? 0. So my sustainable yield as a function of v at v equal to 0 is 0. And let me take... So this is the tangent at the point. So this line I can call v critical times x. It's a critical value because for v less than v critical, I get a sustainable level. But at v equal to v critical, I'm down back at this point. So if v is less than v critical, then that's my equilibrium. And as this increases, so the equilibrium reaches a maximum. And through here, this I can call v msy. And the corresponding x is x msy. So as I increase v, I go from 0 to a maximum. And then I start going down until I get to this critical value of v. So I'm going from 0 through v msy to this critical value of v. And I start at 0, and I hit a maximum, and then I go down to 0 again. So you see that the sustainable yield effort curve looks very much like the function f of x, but this is a function y of v. So these two functions look similar, but they only look similar because f of x has this nice symmetric shape. If f of x doesn't have this nice symmetric shape, then what happens? So what I'm going to do is I'm going to look at the case where f of x, this is what I call critical depensation. And so in this case, the function f of x looks something like this, and I can call this v1, and I can call this v2. Sorry, x1 and x2. In fact, what I'm going to call this is capital K and little k. So those are my two equilibria, capital K and little k. And actually, if you wanted to see a model of this, you can see models that dx dt is equal to some r times x, and then it'll be x minus k, k minus x. So this would happen if this were a cubic equation. And we discussed how this can arise if the population actually declines at very low levels because it's a social species and it can't have a positive growth rate because there aren't enough individuals to form a social cohesive unit for it to grow. So in this case, we can look at different values of v, x. So here we have f of x. So we have the same equation, dx dt equals f of x minus vx. In this case, f is now going to be something that looks like this. And so it's a more general model. And so in this case, the yield effort curve is not going to mirror exactly what f of x looks like, but it's going to have some interesting properties. So we're going to plot v and y as a function of v. So does everybody, any questions about this? Does everybody understand what I'm doing? Now's the time to ask. Yeah? Okay. F of x is the right-hand side of the differential equation. It's our model about population growth. It tells us how the population grows. And in the case where it's symmetric, then we've written down a symmetric model, which we call the logistic model. So when f of x is equal to that, we have this symmetric logistic model. Now this is how the population grows when it's not being harvested. If we harvest it, we take out numbers or biomass at a certain rate. The rate at which we take it out, we call h. And h is a function of x, and it's also a function of v. So you can think of it more generally as a function of x and v. If we plot it on this diagram, we say this is a diagram of a function versus x. So we've got this function versus x and this function versus x. For different constant values of v, we're going to have different points that will lead to an equilibrium. The equilibrium conditions require this to be equal to that. So we look where this is equal to that, and we say, at that point, how much yield would we take out if the population were at this equilibrium and we were applying this value of v? So if we're applying this value of v, actually it's better to put subscript v here because it depends on the value of v. If we're applying this value of v, then we can have a sustainable yield for all time at this level. This level we call y. So that's our sustainable yield, or our equilibrium yield. So in mathematics you would say equilibrium yield. In resource economics you would say sustainable yield. So people just have different vocabularies in different subjects. Okay, does that answer your question, or do you want to follow it up? Any other questions? It's very good to ask questions because you can't follow what I'm doing if you lose the thread. Yeah. So this would be the carrying capacity. In this case, the carrying capacity is K. In a more general model like this one, we have a carrying capacity K over here, but we also have a critical value, little k. And when the population drops below little k, it can't grow. It can only decline. And this is 0. So this is a more general model. And if you look in the calculus textbook, we talk about this in some of the exercises. I'm not sure if we have an example on it in the main text, but what's important is for you to understand graphically what's going on, because this is all you can understand graphically. Yeah.
So are those two calculations?
No, so let's draw. I'm looking at two cases. Okay? Yeah, so there are two different types of populations. For case 1, I have two plots. I have a plot that helps me understand the dynamics, and then I have my equilibrium yield effort curve that arises from here. The thing about these two plots is that they're a little deceptive because the plots look the same. But here I'm plotting f, the growth rate, as a function of x, and the harvest as a function of x. Here I'm plotting the sustainable equilibrium as a function of v. It's the same v. So we're connecting up in that way. Yeah.
Are all y values on the second plot?
Yeah.
Are those all sustainable?
They're all sustainable as long as v goes from 0 to this critical value. At this critical value and above, there's no longer an equilibrium because this curve does not intersect that curve. So there's no longer an equilibrium. So that's why it goes up and it comes down to 0. Okay, now this is very good to ask all these questions because I'm sure it's clarifying a lot of things in your mind. Anything else? So is everybody clear? Yeah?
So what would be like an example of population that would go through that?
An example of a population like this? Well, that's usually a population that is highly social in some way. So, for example, one of the examples I gave was people thought that very large whales, when they get below a certain critical density, can't find mates, and so they can't reproduce effectively. In other societies that require, like, a strong social structure, troops of baboons, they defend themselves against leopards. And if the social structure got too small, then they couldn't defend. They have to have, like, 3 or 4 big males in order to keep a leopard at bay. But so if you go and look at a population of baboons in Africa and some park or somewhere, there'll be different troops of baboons. And a troop might consist of anywhere from a dozen individuals to actually up to 100 individuals. And as the population gets less and less, more and more scarce, so because they're based on kind of family structures, they'll get smaller and smaller. If different groups try to combine, eventually they'll sort of boil down to one group, and then the males won't be able to go out to find mates to breed somewhere else, so you'll get inbreeding. And so as the population gets smaller, inbreeding comes in, and we know that inbreeding can cause deleterious mutants to express themselves, and so you have all the problems that you get with inbreeding depression. So that's why low densities are usually bad. Yeah? Yeah. No, it gets to, this is the density of the population. So it says, if the population is at very low densities, it declines rapidly. When it gets to a certain density, it can start to grow. This is the growth rate. So over here, the population is declining slowly. Over here, it's growing slowly. Then when it reaches this level, the density-dependent effects kick in so that the growth rate per capita starts to go down. Or the total growth rate starts to go down. So this is an expression of the right-hand side of the equation, f of x. So that's why I've got f of x over there. Now, against f of x, I want to plot h equals v times x. So here's v times x. And you can see that this is v1x, this is v2x. v1x has an equilibrium, let's say, at x1. v2x has an equilibrium in x2. v1x, when you're at the equilibrium x1, will give you a harvest rate h1 equal to v1x1. So this is h1 equal to v1x1. And over here, this is h2 equal to v2x2. And so you get these different values until finally you get to a critical point. So I'm going to draw two v's here. This one is v MSY. And the corresponding x is x MSY. And the corresponding h is h MSY. Now these h's when these h's are in equilibrium like this, I'm calling them y, because it's a sustainable yield. I don't want to use h, because I use h more generally to say a harvest, which might be time dependent or not. In the case where h is constant and the population is constant because I'm applying v1 when the population is at x1, I'm just getting a constant yield, which I could call y1. So, but this is going to be, as I change the value of v, so this will increase and then it'll start to decrease again. So what will happen is it'll start to increase, it'll reach a maximum at v MSY. This is v equal to 0, and then it'll start to turn over. Now something really interesting happens when I increase v until it becomes tangent to this curve. And I'll call this v critical, or this is the critical value of v times x, and you can also say that's a critical value of x. This is below the MSY value. You can call this h critical if you want. H critical occurs when I apply v critical in the model until I reach this equilibrium x critical, and x critical times v critical gives me h critical, which is the point at which, if I increase v above this, I no longer have an equilibrium. So what happens is that over here, I cease to have an equilibrium at v critical. So you see this increases, reaches a maximum, starts to come down, and at that point, I cease to have an equilibrium. Now before that point, you can say there's actually two values of x. There's, like for example, over here, when I'm applying v2, I have x2, but I also have x2 dashed. So I get two values of x. If you apply your stability theory, you'll see that the slope of the curve there is positive, while the slope of the curve there is negative, when you evaluate that with respect to this line, so that when you take the derivative of the right-hand side, you can show that this one is stable, and that one's unstable. So in order to indicate that, what I do is I say that, actually, for every value of v, I get a stable equilibrium and an unstable equilibrium. So I get something that looks like this. So I put a dotted line in to show that this is also an equilibrium yield effort curve, a part of the equilibrium yield effort curve, but that equilibrium is unstable. So if I perturb it, I'll either